Right. So Cockroachdb is a database written in Go, and this is the Go dev room. But just as an announcement, I won't be talking about any of the individual code at all. What I want to do instead is take you on a tour of the ingredients and the design principles that we have put together to build the system, and hopefully to convince you to actually check out the source code, maybe look at it, contribute, do whatever you want with it. But today, going to be about design of databases, but I'm hoping not to lose any of you. So if it gets too fast or something like that, I'm in for leisurely pace, so ask questions at any point. Before I talk about the juice, let me just motivate why we're building just another database. I mean, there's so many of them, probably a new one every day. And we're in this race, so to motivate why we're doing this, let's look at the very, very simplified history of databases for the last 30 years. So of course, there's SQL. Everyone knows it. It doesn't scale really well, and replication, safety of your data is kind of an issue as well. So when the 2000s rolled along, people started realizing that they needed something else. And of course, that something else goes with the umbrella term NoSQL, which can mean basically anything except pure SQL. But what you generally understand under a database that follows this paradigm is that it is very scalable and places high importance on availability. And usually that also means that in the process, you lose consistency. You don't have transactions anymore in many cases. Or you have something that tries to compensate for the absence of real transactions, and you do kind of workarounds like compare and set. So eventual consistency, manual joins, kind of issues with data integrity across your cluster is something that you experience in those databases. And then there's like a third generation that's been popping up just for the last, let's say, 2 to 4 years, which I would just dub new SQL. And that's something that tries to combine both of the advantages of the two previous eras. Them being scalability, high availability, and transactionality, which means like SQL properties. And since this is Go, and Go is very connected to Google, let's just look at Google themselves. So pre-2004, a lot of projects were actually running on standard SQL databases, so we had things like sharding, and it was not that pretty. AdWords, I think, had big issues with it. And so everyone was pretty happy when Bigtable was invented at Google, which was basically your standard NoSQL database. It's just like a column store and had eventual consistency, very highly available, very scalable. And that was a big, big step up from the previous SQL stuff. But only 2 years later, people had realized that you would actually want data integrity at many points in your apps, especially if you have a platform database that a lot of products use. It's kind of cumbersome if each individual programmer has to think about the issues that could happen if that data that they wrote here isn't there yet. And it's really complex. So what Google did was basically to put another layer on this NoSQL data store that they had, and that layer kind of emulated the consistency that you needed, which is a good step up. And I would call this like a NoSQL-ish database. But it had its downsides because the underlying data store was not designed to do stuff like this. It was fairly slow and complex. And then it took another 6 years for Google to come up with their magical bullet, which is called Spanner. And that's really a semi-relational, fully linearizable database, and doesn't really matter what that means, but it basically behaves like a single Postgres on your single machine. Your app developer doesn't have to think about which transaction isolation to use or whether anything's inconsistent. You just use it, write your applications. You have transactions that you can use whenever you need to update things in that belong together. And so that's really, really what they use today. And I'm pretty sure like most new stuff will try to go there as well. And there's one very telling quote from the white paper on Spanner that Google published in 2012. And the quote is that, well, they believe it's better to have application programmers deal with performance issues due to transaction overuse sometimes, but that's way better than not having transactions and having to deal with it every single time you need one. So this is really the reason for Cockroach's existence. We really want someone that's not Google to also be able to have this. So right now, Spanner is at Google and probably works great. Maybe some of you guys know. It's scalable, highly available, transactional, but you cannot have it because it's not open source. There's a lot of auxiliary services. It really kind of plugs into the Google infrastructure ecosystem, so it's nothing you can use. And what we're doing with Cockroach is building a system that kind of gives you the same stuff, but is not as much tied into this infrastructure and also has a very, very different design underneath. So it looks kind of the same, but don't be fooled. It's not a clone of Spanner. It's actually something that just winds up giving you what Spanner provides to Google. So if you were here at 9 a.m., Kelsey also mentioned that CoreOS is trying to build you stuff from Google that you can just download. we're kind of trying to build Google's database that you can just download. And of course, open source. So let's talk about what we mean by availability. Cockroach, if you know the CAP theorem, then you know that you either have to be CA or CP, or you screw up and then you're neither. Cockroach is trying to be a CP system, and that means that each piece of data that you write goes to a bunch of replicas. And the choice of being consistent means that a server will not work unless it knows that what it's telling you or what you're asking it to do is happening on the majority of replicas. So if you have 3 data centers and 2 data centers go away, then you're really screwed, because that one data center will not be able to talk to the other 2, and 1 out of 3 is not a majority. If you have 1 data center going down out of the 3, that doesn't matter because there's still 2. So this is kind of the basic idea. And so you can see it's not as ultimately available as a NoSQL data store that basically just answers you with whatever data it finds, but it's still highly available. You need a majority to disappear. And really, the only price that you pay for this is you have to actually acknowledge that the stuff that you write is on a majority. So that gives you a certain latency for your writes. And of course, when you do reads, you also have to make sure that who you're reading from is actually in charge of knowing which one's the up-to-date data. So there's some latency that you have to pay. Spanner does that too, and that's just a fundamental truth of having consistent data. You cannot just read it without checking. And so, as I said, if your data center goes down, the app shouldn't notice at all, because the app shouldn't know anything about the database behind. It doesn't have to track where the data is, because the database is completely consistent, and no matter which entry point you choose, you always get the exact same state. So if I usually access like this server in data center 1, because that's closest to me, and that suddenly doesn't work, you're just like, fuck that, I'm just taking another one. And you get the same thing. And one word of caution here, building a CP system, so building a system that's consistent, that's really difficult. I mean, distributed systems are always complicated and very prone to errors. And if you have to do something like that in your app yourself, it's very likely that you run into trouble and that there are subtle bugs. Think about it, it's kind of the same as trying to do your own encryption in your app. I mean, you can do it, and maybe it looks pretty good, but it's probably something that's wrong. So really, we think the database should take care of this completely. So, and really the main point with Cockroach is that it's a very transactional data store. So what we want you to be able to do is to run everything, any operation that you can run on your data store, you run it inside of a transaction, and then it is completely isolated from the rest. I will talk about specific isolation levels later. And having transactions, of course, like the obvious benefits, your applications get much easier. You just really write what's happening, wrap it in a transaction, you're done. You never have any problems with bigger updates running to like 50%, and then something crashes, and then you're like, oh, damn, you need to clean this up. It just doesn't happen. Either everything happens or nothing. And another thing that we're trying to address with Cockroach is kind of this image of transactions as being very fat and having high overhead, and that really that's already a reason not to have them. No, I'll actually talk about our implementation of transactions a lot today, and I'm hoping to convince you that it seems very lightweight. It's not like you incur a huge overhead just for having transactions in this database. And yeah, so what we do with Cockroach is we have a very, very high default. So if you can like have anyone who doesn't know anything about isolation levels just use Cockroach. It will be fine, because the default isolation is so high that everything works exactly like anyone think it would. But we acknowledge that there are certain situations where you might have bottlenecks. And for that, we have one isolation level that's slightly lower, which is snapshot isolation, which I guess is pretty well known. And that can be used if you have specific use cases that actually have a lot of contention, which means a lot of transactions kind of battling the same key space. Okay, high-level architecture. So what kind of database are we actually building? So really what it is at the moment, or what it is at its core, is a sorted monolithic key-value store. So everyone knows what a key-value store is. Sorted key-value store means that the keys in it actually have an order, and you can scan for keys in that order. So you can say, I want all the keys from A to B. And monolithic means that it's a distributed system, but it doesn't matter which entry point you choose. Logically, it represents a single key-value store. So there's no different versions of anything on different servers. You always get the exact same state. Okay, some of the basic ingredients that go into it on a lower level are RocksDB. That's for storage. So that's actually for storing key value pairs on your hard drive. On each hard drive, you have one instance of this RocksDB thing. And that's a log-structured merge type tree data store. It doesn't really matter what it is, but it's fast. It has very high sustained write throughput, and it's actually Facebook's fork of Google's LevelDB. Okay, so there's nice people working on this, and it's a great thing, and we use that. And if you want to read more about it, just go ahead. So then the actual design choice that we made according to your data is that, so we have the sorted key value store, and we basically logically encapsulate 64 megabyte chunks of data, more or less. So the whole key range A to Z will basically be split into different parts, and each part will represent about 64 megabytes of data. Not precisely, but more or less 64 megabytes. And those units kind of deal on the form consensus groups. So they, on that level, you get your consistency and replicate the data on different nodes. If one of the units gets too fat, it will split into 2 units. If many units get very small, it will fuse into a unit. So this is called a range, and this is really, if you read the design document, it's all over the place, because that's the fundamental unit of replication and encapsulation in Cockroach. So as I said, each of the ranges forms a consensus group. So each range, the data in each range is on typically 3 replicas, and those replicas join together with a consensus algorithm, which basically elects a leader among them, and that leader will then advance the state machine on each of them. This is a topic for another talk, and I will just say that we're using Raft, which is a very popular algorithm today. Before, usually you use Paxos, which is, I think, way more complicated and prone to subtle implementation errors. And we actually put a lot of work into writing a Raft implementation. We found that none of those that existed were meeting our needs. And CoreOS at the same time had an issue with GoRaft. And so it was just natural for us to team up. So basically, we contributed some code to them that basically made sure that the implementation that they have is also OK if you have, say, 100 servers with millions and millions of consensus groups. Because that is happening with Cockroach. You have 64 megabytes pieces of data, each a consensus group. And then you have millions of those on a node if you have a hard drive that's really big. So this is really an interesting thing. And it also needs very careful optimization, because if each consensus group talks to each other consensus group, then you have millions square connections, and you're done already. So this is interesting stuff, but I just want to mention it now. We also have a concept of causality, so we just don't use machines' individual timestamps. If you have looked at distributed systems, and you know that tracking causality is one of the major issues, because any of the machines will have a clock that's not like any of the other machines. Google's approach to this is actually put GPS and atomic clocks everywhere, and then have an API that basically tells you what your maximum offset is. And based on that, they do everything. We don't want to do that, because we want you to be able to use this thing, and you probably don't want to do atomic clocks. So what we do instead is we have a hybrid logical clock, which is also a fairly recent paper. I'm sure we have a link on our website. And basically what it does, it orients itself on the wall times of individual nodes, but actually causally connects all the events that somehow interact within the system. But think of it as a timestamp with an extra logical component. And really the core part, I would say, that I want to talk about today is lock-free transactions. So with Spanner, with Google's product, you would just use locking to do the transactions in central places. And then you would use a good time signal to be able to get your consistency. We cannot afford that, and we don't want to, because we have a lock-free implementation of transactions, which I will talk about in detail. And that's kind of the scope for the beta release, which we're putting out hopefully soon. So I would say we're probably about 90% done. So you cannot use Cockroach in production yet. I'm sorry, but we're pushing hard to get there in due time. And once we have that, so once we have our sorted, distributed, great key value store, we actually can put a structured data layer on top, which is basically an abstraction that talks about tables, columns, indexes. And once you have that, SQL. This is kind of standard stuff, exactly how Google built Spanner. So you have a key value store, and then you extract twice, and you get SQL. So that's, of course, more aspirational right now, but this is really the road that's planned. So here's just a nice picture to get away from the text slides for a second. Each store here is a hard drive in any of the servers. And then each of those colored thingies is actually a range. So that represents about 64 megabytes of key value pairs. And we color-coded the individual consensus groups. So all the red ones, you see there's one on store 1, store 2, store 3, are actually a logical unit. So they will strive to hold the same data at all times, and they are actually a Raft consensus group. So if you count consensus groups here, there's 1, 2, 3, 4. In reality, of course, you have millions. So that's basically what the data looks like on your disk. Okay. So this is a part of the presentation I actually wanted to get to. So we're building this database, but how does it actually look like if you run a transaction? So what actually happens? And I have one text slide, and then I have a graphic to hopefully iterate twice and actually put it into some of your heads. So really what we do is a variation of a two-phase commit. So if you are a transaction and you're writing, then you're not writing actual just values and you're leaving them there. You're writing values with a special flag. That flag basically tells everyone else, hey, look, this is a transactional value, and the transaction might still be running, and this is transaction ID. There's also a central system table that every transaction registers in, and which serves as a single source of truth. So you have basically the system key space right here, which says which transactions exist, and you have the values that are written by transactions, which are intents. So if your transaction starts, it writes itself into a transaction table, then you do your business, you write a lot of stuff that will end up as intents in the key value store, and then you want to commit. So what do? So you can think of two things. So either you just write to the transaction table, hey, I'm committed, and then you could think about going to all of those previous intents that you wrote and changing them all to honest values because you're now committed, and only then return to the client. And if we did that, then I would completely understand if you said that that's kind of a no-go, because if you write 100 values, then just to commit, I have to write another 100 values. No, but really what we can do is just commit the transaction, leave all those intents, return to the client. The client is free to do whatever they want. And only then we kind of, on a best effort basis, we go to all of those intents that you wrote and change them to honest values. And the reason why this is still correct is, well, assuming that this intent cleanup failed and someone else would try to do something with the key that you wrote your intent to, well, they will see an intent, and they will know which transaction wrote the intent because that's saved in the intent. So they will just have to go to the transaction table and check on your transaction. And because that transaction status right here is authoritative for the actual status of the transaction, it's atomically updated. There's no ambiguity. If it sees it's committed, then it can just clean up the intent and read the value or not, depending on if it worked, and then do its business. So if you look at what would change if we didn't have transactions, the only thing that you lose are two writes to this transaction table and the best effort cleanup, which is not blocking the client. So this in itself is very lightweight. And because text slides suck, I try to come up with a picture that says the same thing. So how do we read this? So time goes from the top to the bottom. So what happens further to the top is earlier. And so basically you start here. So you're a client and you're just like, hey, I want to start a transaction. And the server's like, cool. And then what happens is that in this transaction table, which is this column right here, there will be an entry written, which basically says, well, the transaction with transaction ID T1 is now pending, which means it's running, and it was started at this time. And time is a logical timestamp. It's not your standard wall time. And then your client wants to do certain things in this transactions. Let's assume you're just trying to write 2, 3 keys. And so as I mentioned before, the transaction will write those intents. So it will write the key and will write an intent associating the value and the transaction that wants to write it. And then you do this a bunch of times. And then at some point you want to commit. So you basically try to update your transaction table entry from pending to committed. And once that happens, you go to the client. And then the cluster will try to just look at your intents that you wrote and upgrade them to honest values. Okay? Who understood this? Yeah. Yeah, great. Some hands. So that means everyone got it. Okay, and then there's some. And now that is. You have a question?
Yeah, I have a question.
You want to ask it now? Sure, go ahead.
So what you're doing in effect is lazy replication.
No.
Well, if you've got a distributed system, how do you distribute those?
So yeah, so you're wondering about how those things get to all the other nodes.
Yes.
So actually, this is already on the monolithic key value store. So if you write something here, when it shows up, it's actually replicated.
Ah, right. Okay.
So I should have mentioned this, but this really, because I'm trying to talk about transactions, I'm trying to take the raft thing out for a second. But really, if you write an intent, it actually ends up on at least 2 replicas, and then the third replica will eventually get it maybe. But it's really consistent already, because otherwise we wouldn't have any chances, right?
Right. So how do you? So I'm interested in the time space between having some replication that you've done in your intents and the third one, because if, for example, example, you're connected to the third one. How do you find out that in fact your third one is out of date?
Well, with standard raft, you always read from the leader, so that will not happen.
Right, okay.
But there's a concept called leader releases, which basically gives timeshares to who the leader is, but basically, morally, you read from the leader.
Don't worry.
Yeah, so this is what you're asking is basically a raft and consensus group question.
Oh, right, okay. Thank you.
Okay, so so now hopefully it's kind of clear what, yeah?
I was wondering if you do you defer the cleanup to compaction time?
No, we do the cleanup. So
Repeat
the question was if the cleanup is done way later at compaction time or if it's done right away. Is that correct? It's done right away because you don't want a lot of clients to run to those intents, because every time they do that, they actually have to go to the transaction table and then clean up the intent. So of course, our compaction routines, they also clean up intents, assuming that they're still there. I mean, it might happen if no one actually ever uses the key. But really, basically what you do is commit and then immediately you go to the intents. Okay, last question.
Serializability?
This is serializability, yes.
So it's based on write snapshot isolation, right?
Yeah.
Okay.
So if the same client read the data, say you want to index it
Uh-huh.
after written, is it guaranteed that they see this actually?
The transaction sees its own rights, yeah.
No, after the transaction.
Oh yeah, sure. If you commit and then you read right away, yeah, of course you see it. Because I mean, the worst thing that happens is you read your own intent, but then you resolve your own intent.
But I leave transaction already. After I did commit,
Uh-huh.
not inside my transaction. As
Yeah,
a client,
yeah.
Same client.
This after anything that happens in absolute time after this will see your values. Otherwise, it wouldn't be serializable, right? And what's happened is, in the worst case, you see an intent that hasn't been upgraded to a value. But then you will be like, oh, this intent belongs to T1. I will check on T1. Oh, it's committed. So this should really be a value, and then you switch it. So there's some awful. So people who read the data actually clean it up while they do. But we obviously make an effort to not have them see those. So we clean them up as fast as we can. Okay? So any further questions, I will be happy to take them at the end, but I don't want to run out of time. Oh, hold on. I wanted to say two things. So this is, of course, the case in which nothing goes wrong. But we're doing lock-free transactions, so a lot of things can go wrong because transactions will actually be writing to overlapping key ranges, and it's very interesting to see what happens. So for the first time in a talk about Cockroach, I'm actually going to try to explain this to you. And before I go to the next slide, which actually deals with the conflict resolution, I just want to mention a few things that can happen. So I don't want to get into the timestamp internals too much, but really what's very, very central to a transaction, it's this timestamp here. So think of this timestamp as the provisional commit timestamp of the transaction. So when you start with kind of the current timestamp of the node, and then you do a thing, and then when you come back to this timestamp, it's very possible that some of the writes that you did will actually have increased it, or that another transaction will have increased it. It will never decrease, but it might increase. And if the timestamp didn't increase, then that logically means that all of your writes and reads happen at the same time. And if you commit with that, you will be serializable. If you allow your timestamp to be pushed, increased, and you commit, then what you will end up with is snapshot isolation. So if you know those two things, then I just want to tell you that the only difference between the two isolation levels in Cockroach is whether you allow this timestamp to be pushed. That's the only difference. So there's no completely two systems of transactions that we have. There's really a single system, and just the committing behavior is different. And of course, in when you have conflicts between transactions, they also take the course of action depending on what type of isolation which one has. But it's really, really lightweight. Okay? So let's look at things that can actually go wrong. And what I want to focus on is what happens if you read something that doesn't seem right to you, or where you're not sure what to do. Write conflicts are easier because usually you'll just have to restart or abort someone. Okay, so assuming we're a transaction, and in this great picture here, we want to read at this time. And this is a single key, and we're using an MVCC system, so there are a lot of versions of this key potentially. And as before, well, I guess it's the opposite of before, newer versions are on the top. So this version here is very new, and this version here is very old. And we're reading at this level. And now you could say, why is this going to the future that much? Well, I want to really point out that you can actually see future values. So on your node, you can see values which have a timestamp that's higher than what you think now is. And that's simply because we have a distributed system. If you have a bunch of nodes, and one of the nodes' clock is fast, so it's in the future, and it runs a transaction, then it will run that transaction at its local time when it starts. If that is sufficiently ahead, any writes that it does will be at that timestamp, which might well be in that node's future. Okay, so you can definitely see future values here. And now if you're a transaction and you want to read at a timestamp, what do you do if you see a value that's in the future? I mean, do you want to read it or not, or do you restart? And really what you should be doing, and this is one of the parts where actually clock uncertainty, the absolute time uncertainty comes into play, is you have to decide if the value is close enough to your own timestamp to actually have happened before your timestamp. So if something just happened, if you're reading at time 10 and something happened at time 11, and you know your average clock offset or your maximum clock offset is 5, then you can't really be sure if in absolute time this guy was here or here and whether you should be seeing it or not. So really what you have to do in this case is come again. And you will come again with a timestamp that's here. So that will be one case in which the transaction's provisional commit timestamp actually increases, and you will have to restart the transaction, which is a retry is pretty lightweight. It's not the same as an abort. And now you could say, okay, but what happens if one single node that's in the future actually hammers the key with writes, and I'm trying to read this key, so every time I come back, there will be a new value on top, and it will never end. But that can actually not happen because we can make it so that we only restart once per node that caused the conflict. So when you read a key and there's someone in your near future, per node that wrote it, you only restart once. So normally you only do one single restart if that happens. And then the other thing that can happen is if you see something in the future, but it's very far in the future, and because maybe in your cluster the clocks differ only by 100 milliseconds at the most, this value cannot possibly have happened before your read, and so you can safely ignore the value. So those are two things about the future. If it's far in the future, you don't have to read it. If it's near in the future, then you usually need a restart, and you need to slip past that value. What happens if you read something in the past? Well, if it's an honest value, I mean, it's a value. It's an MVCC system. You're reading the next candidate, so you just read the value. If there's not a value but an intent, well, then you have to check, because it could be an intent from a transaction that's still running, in which case you want to restart yourself, or push that intent into the future, which you can do for snapshot isolation transactions. So you basically want to change this value so that it's actually here, and then it's not your problem because it's in the future. Or if you find that the intent is just something that hasn't been cleaned up yet, so the transaction has committed, then it's a value, so you upgrade it to a value and you read it. Or the third case, the intent belongs to a transaction which was aborted, so the value isn't there, so you delete it. Okay, so basically, certain things can happen, but in any of the situations, it's clear how you go about it. No, I'm not going to ask again who understood this. Okay, but if it kind of made sense and you go to the design documents, there's like long paragraphs about this, and if you look at it for a while, it should make sense.
I was just wondering, values in the far future are
Mhm.
because you want to read in the past.
Yeah, you want to read at your timestamp. So really, you want the value that's the next value that's down here.
And you didn't want to have two separate APIs, one to read from the past and one to read from current time, so that you wouldn't have to guess where the...
No, I mean, it's because you're a transaction. If you're a transaction, you want to do everything at your transaction timestamp. If we were in a transaction, you would actually just read the highest value that's actually there. So if you find a committed intent or a value, then you would read that. And otherwise, if it's still open, you would not read it. So if you're not transactional, all this is vastly simplified, because you will always just read at the current node's time, which guarantees that nothing's ahead of you. Okay, but this is unfortunately, it's still, like, being as sleek and lightweight as it is, it still gets complicated if you dig into it deep enough. But hopefully that gave you a small taste of it. So, and let's briefly talk about the isolation that you get. So, as I said, we opted for serializable snapshot isolation as a default. And that's basically just, if you don't know about this stuff, it's really just how you think it should work. That's just basically what it is. That's what you want. In an ideal world, everyone would just be using serializable or linearizable. There's a subtle difference, which I will not explain, except that linearizable has to do with absolute time, and serializable allows that transactions always seem to be happening in a non-overlapping fashion, but they might switch sometimes. You could run one transaction, then run another one, but the commit timestamps would actually suggest the opposite. And that will usually not happen in Cockroach, but it might happen if you have two separate clients working on completely non-interlapping operations on different parts of the cluster, and if your timing is really, really weird, then that could in theory happen. I'm pretty sure we couldn't even reproduce it in practice because of the latencies involved, but theoretically, Spanner, which gets linearizable, is doing something slightly stronger. But we have a flag built in that basically just takes the maximum clock offset and makes sure that the time passes between two critical operations. So if you add this flag, then Cockroach will be serializable. And you just have slightly longer transactions depending on what your clock offset is. That also opens up an interesting venue, because it's quite conceivable that AWS and all these other cloud providers might actually just provide you with such an API. Like AWS, they can put an atomic clock in your data center. They don't care. And then once they have a nice API for this, so basically, let's think of an open source true time, Cockroach could just hook into it and control the system maximum clock offset based on this. And that would mean that you basically get Spanner because someone else is doing the infrastructure part that you cannot get rid of, which is time for you. OK? So serializable snapshot, standard, great stuff. And the only thing with it is, so the way it works, if you're in a snapshot, a serializable snapshot transaction, you want to commit, then you cannot commit if your timestamp was pushed forward. Because that means that, it doesn't matter, but it means that you could maybe not be serializable. And that could lead to a lot of restarts. So if you imagine having a huge amount of transactions just kind of fighting over the same keys, then you could conceivably see a lot of restarts, and maybe that would be a problem. And in those cases, you might want to downgrade to snapshot isolation, which snapshot isolation is probably pretty well known. It just means that a transaction during its lifetime always sees the data that was present at the time that it started. And that's also already a fairly high isolation level, but it breaks a lot of some things. For instance, constraints can break because you're basically reading data that might have been updated by someone else, and then you're relying on data that they upgraded in the meantime, and you can lose some things, but it's also fairly good. So you really cannot do really shitty consistency with Cockroach. It just doesn't work. You cannot do it. Or you can just go outside of a transaction, then write individually, I guess. OK, so those are the two. And I will actually leave you with that. So basically, summary, Cockroach is really inspired by Spanner, no doubt, but it's very different from Spanner. Just like the design components that go into it are much more sleek and lightweight. And we're actually in an interesting part in the project. So I would say about 90% done to getting the first beta release. Beta meaning that that's something that would actually encourage people to try to run and see how it works for them. Not in production, but moving there. We're a fairly active project, but we appreciate any help that we can get, especially like if there's very skilled Go people here. It doesn't matter if it's tooling or code reviews. We're really happy to have you look at this stuff. And usually the way it works, once you contribute a couple of small things, you usually end up being dragged thinking about distributed system things, which in itself are really interesting. I personally enjoyed a lot, and I would be happy if you checked it out or ask questions. If you want to kind of a human readable description of all this, if you don't want to go through the source code and try and piece out what's happening, and also learn about all the other components that we have, because obviously I omitted a huge bunch of features and design decisions, just click this link and you will basically get the initial version of the design documents, which was written by our mastermind, Spencer Kimball, who's an ex-Googler, worked on Colossus. So there's basically some knowledge in our group behind building systems like these. And if you're now hooked on the CP and distributed systems train and you don't know this block here, then just read it, because it's fun. Someone just like spins up a bunch of different databases and breaks them just by fiddling with the network just a little bit. And that is all I want to say today. Thank you.
So I have one question
Uh-huh.
to give some tangibility to the Go part of the whole presentation.
Uh-huh.
Like you're always running against time when you're implementing a transaction or something like this, right? And when you're doing things in Go, you have always to handle, especially when you have time constraints, you have to handle the garbage collector. So what are the strategies or tactics? What have you guys done in order to curb the interruptions caused by garbage collector?
The good thing is that we don't have to worry. So the question is whether we can have problems with the Go garbage collection, because you never know if your thread pauses for a second, and that stuff that can happen. And the question was whether we thought about this a lot and what we're doing against it. So currently we're not actually thinking about it, because we're not relying on the time signal for correctness. So what can always happen, of course, if the garbage collector freezes us for 5 seconds, then it will suck because nothing's going to happen in that time. And that will cause transactions to time out, transactions to run to conflicts more often because they will just be running longer. But that's just how it is. I mean, that will just mean that you have a little more contention, you lose a little bit of performance, but it's unfortunately is not critical to correctness at all. So it's definitely something that we will try to optimize as much as we can. But at the current stage, we're just like valuing like integrity and ease of use and ease of reading the code over, you know, like optimizing the critical paths yet. But that's of course something we're going to do eventually.
Generally less garbage.
Mm-hmm.
Is anybody paying you to work on this? Who's behind it? Is it all just
So up to this point, it's actually, the question is, thank you. The question is if we get paid to do this. And the answer is slightly complicated right now because in about a couple months' time, the answer might actually be different. So it's very conceivable that Cockroach will turn into a company that's centered around its open source products. I think of something like CoreOS, like basically cool guys that like go and do cool things. So that's something that you might want to watch out for. But as of today, we're all doing this for free. Back there?
The transaction table is a component which is in the client patch all the time. Can you describe more the design of it?
The transaction table, the client knows nothing about the transaction table. Oh, the question was kind of where this transaction table is and if the client has to know about it. So no, the client actually doesn't know it. The transaction table really lives on Cockroach's key space. So basically just what we do is we separate off a small bunch at the beginning, which we need to do anyways because we need an addressing scheme to kind of map keys to nodes that actually have this replica of the key. And so basically just think of it as being \0 \0 txn and then the transaction ID. So it's something that lives on the server and that's managed only by so-called transaction coordinators, which is basically who you're talking to if you're a client running a transaction through Cockroach. So it's completely not something we want in the client. Our clients are actually, so of course we have a Go client, but people have started writing a Scala client, I think a Node.js client, and really the clients don't do any of the work. They just need some simple retry logic and not actually deal with the transaction. We have all of this in the base.
So does it link to
No, go.
Does it live within the one graph consensus group, or can you distribute this transaction table across multiple?
Every single, so there's some pieces of data which we actually write to the local node only, but that's mostly accounting and stuff like that. The transaction table is completely replicated. It's replicated exactly the same as any other key. And that's completely necessary because you cannot afford to have different versions.
Across multiple ranges.
No, but one range, well, of course it can, yeah, sure. Yeah. Everything can span across ranges, except for the very first addressing scheme. So if you want to look up a value, you always go to the beginning of the key space, and that always has to be in one place. But we actually splitted the addressing scheme to find the range that actually holds your data into 2 levels, just to be able to scale out to like 4 exabyte or something. So it will always fit there.
I was wondering if the state of the location of the ranges were kept by graph protocol and kept in memory, or do you have some kind of made a data table? But I think you can look at it right now.
Come again?
I think you just hinted it at this right now.
So yeah, the question, if I understood it correctly, is how Raft stores its data. So how we deal with the Raft log and the state.
Yes.
Okay, that.
So if the placement of ranges is purely maintained by Raft.
No, so the placement of ranges is really, I mean, Raft knows where the ranges are, but it really only knows the range through its node ID. And because the ranges itself are participating in Raft through their node, there's really never any question of where they are. And what we do with the Raft log is, that's actually a big part of the work that we did together with CoreOS on Raft. We made sure that we can actually store this in our Rocksdb underlying storage. So we made sure that the Raft implementation has interfaces that you can just implement for snapshotting, compaction, and compaction is here truncation, and of course the storage of the log. So that completely goes to Rocksdb on those specific nodes, and that of course is not replicated because each.
But logically, it belongs to the Raft consensus since you have one Raft consensus for each single range, except for having it for each single logical member of your cluster.
I'm sorry, I'm still confused by the question.
So basically, you store the raft log
Uh-huh.
on your own storage layer.
Yes,
So
yes,
you
yes, yes.
map the range and node.
Well, you know, each member of the group lives on one node, and it will just use a local storage in that RocksDB instance on that node and just key it by its raft ID, which is unique. So basically, everything is just stored on the physical machine that's at. And sure, you have 3 replicas, but they just have 3 copies because that's how raft works. Yeah. And the question was where the raft data is stored. I'm not sure about the order. You guys figure it out. Huh?
When you're restarting the transaction, how does it affect the client application? Because some part of the client application is run again.
No, so we try to handle, so because we're doing lock-free transactions, it's understood that transactions may restart, and that's not actually an issue because it's expected. So we shield as much as that of that away from the client as we can. So usually, if you're a client, you send a transaction, it might bounce a little bit, but then it'll come back. So usually, you don't know. Some of the restarts will be transparent to the client, because otherwise, we would have to have the retry logic in the client, which would be hard. What?
The client is doing some reads and updates within one transaction.
Mm-hmm.
It needs to read again.
Yeah, but you know, the transaction is kind of ephemeral. It only exists through its entry in the transaction table. So you can read and write to the transactions asynchronously. And any restarts that will happen will just, happen. And only when you commit is the only point where you could actually be affected by the restart adversely is when you commit and you see too many restarts internally so that it will come back as aborted to you. But most of the restarts will really shield from you. There's, of course, very few ones that the client has to handle, but generally the client shouldn't see them. I think you had one? Yeah?
I think you actually touched on that now. So what happens if during a transaction you have a lot of updates to the data? Does the client get an abort that the data changed?
So your question is what happens if a client is writing a lot of values and there's a lot of conflicts? Is that your question? Or?
During a transaction, the data changes a lot.
Uh-huh. I mean, if the data changes in a way that doesn't collide with our transaction, then the client doesn't care.
For the same key you update.
Yeah. So I mean, that's what I hinted at. If you're reading keys and those keys have new intents or they changed, then you have the kind of conflict handling that you saw there. So that might lead to restarts. And if you have very busy keys, then you could end up with a lot of restarts. That's one of the things that you just have to deal with if you're running a system like this where you don't have locking. Things will just, try on their best to get a slot. No, there's not going to be any locking. So what you want to do is you want to go down to either snapshot isolation, which has less restarts, so that might work, or you're going to just have your application deal with this differently. Because assuming you had locking, if you write way more data than you can push through there, then locking is not going to help you because your queue is just going to grow and grow and grow, and so it's the same problem, really. Yes?
So you get the transaction table that issues all the timestamps for the transactions. That's right?
The transaction table has all the information about a transaction, correct.
Okay, but
Not the keys that were written, though.
who issues the timestamps, the logical timestamps?
So when a transaction starts, so I would have to dig a little bit into the timestamps, but basically each node has a so sorry, the question was who makes should just have an NSA microphone into the room and then wouldn't have to do this. So the question was basically where do the timestamps come from? Yeah, so if you start a transaction, then you speak to a node, and that node will take as a starting timestamp for the transaction its local node's logical clock.
Okay.
And that's what's going to be used. So it already answered the question?
Yeah.
So the
Better later.
yeah.
We actually have to finish.
Okay.
But thank you very much.
Yeah, thank you.